Welcome! Today we will finish 5.3, the fundamental theorem of calculus, and I will focus on lots of examples. So the picture right in the middle of the screen here shows the fundamental theorem of calculus part 1. We are actually going to focus on the fundamental theorem of calculus part 2. So remember what it says. If f is a continuous function and big F is an antiderivative of little f, then in order to compute the definite integral from a to b of little f of x dx, all I have to do is compute the antiderivative at b minus the antiderivative at a. So the picture looks like this. This is an area problem where there's some function little f, and I want to compute the area, the net area, could be positive or negative, from a to b. So this is how we did it the old way. I looked at the integral that was given to me and I identify little f of x equals x squared. Then I create an antiderivative, big F, so in this case it might be 1/3 x cubed. Then I have to evaluate big F at the two endpoints, so big F of 2 minus big F of 1, and so that becomes, let's see, 1/3 of 2 cubed minus 1/3 of 1 cubed. So 8/3 minus 1/3 equals 7/3. Let me introduce a little bit of new notation. So it's the same problem, but some new notation that will just streamline the solution. What we do is we start by figuring out an antiderivative. Well, an antiderivative for x squared is 1/3 x cubed. So I'll just write down 1/3 x cubed. Then I put a bracket, or some people just put a straight line, and I'll put the two limits, 1 and 2. And what this notation means is evaluate this at 2, evaluate at 1, and to take the difference. So I start by putting in the 2. So this is 1/3 of 2 cubed minus 1/3 of 1 cubed, which again is our 8/3 minus 1/3, which is 7/3. So it's really the same process as before, but I avoid having to name my antiderivative capital F. That just makes things go a little bit easier. Let's do some more examples. Compute the integral from -1 to 2 of x squared dx. All right. So that equals 1/3 x cubed. Put in a -1, put in a 2. 1/3 of 2 cubed minus 1/3 of -1 cubed. That'll be 8/3 plus 1/3, which is 9/3, which equals 3. -1 cubed equals -1. How about this? Compute the integral from 1 to 0 of x squared dx. So this equals 1/3 x cubed. Integrate 1 and 0. So I plug in the top number first. So this is 1/3 of 0 cubed minus 1/3 1 cubed is -1/3. So my answer is negative. Now maybe that's a little surprising because here is x squared, and from 0 to 1 the area is above the x-axis, but I'm integrating in a weird direction. Normally I go from the small number to the big number. In this case I'm going from the big to the small, so it reverses the sign of everything. So I actually do expect an answer to be negative when integrating from 1 down to 0. What if I have several terms all together? Well, I just handle them all together. So this is 1/3 x cubed plus 1/2 x squared plus 3x, and all of that is evaluated at 0 and 2. So I'll plug in the 2, 1/3 2 cubed plus 1/2 2 squared plus 3 times 2, all of that minus, well, what's going to happen when I plug in 0? 0 plus 0 plus 0. And then we can evaluate. That equals 8/3 plus 4/2 plus 6, and for what it's worth, I think you get 32/3 at the end of that, so 10 2/3. How about some trig functions? Compute the integral from 0 to pi of cosine of x dx. All right, just stop right now. I bet you know what the answer is. Do you? What does cosine look like? Here's my graph of cosine. So just using what I know about symmetry, I have equal area above and below, so the answer is 0. I don't actually have to compute anything. How about this next one? Well, I need an antiderivative for 3 cosine 3x. And be careful, it's tempting to think that the antiderivative is 3 sine of 3x. But if you take the derivative, you'll see that that's not right. Because when you take the derivative, you need the chain rule. The 3 comes out, which maybe lets us understand that, in fact, the antiderivative of 3 cosine 3x is simply a sine of 3x. So that's the guy I want to evaluate from 0 to pi over 6. So I get sine of pi over 2 minus sine of 0. And what is this? Here's my sine graph. Pi over 2, 1 minus 0 equals 1. How about my third trig integral here? Negative 40 to 40, it looks like there's probably a trick, right? Well, sine is symmetric. And so if I go left a certain amount and right a certain amount, these areas will cancel. And so once again, I have a problem whose answer is 0. Now, this next problem, example 7, looks like I'm missing something, right? Well, sometimes you see that and it's a little bit weird. What that really means is there's a 1 in there. So I'm integrating the function 1. What is an antiderivative for 1? The antiderivative of 1 is just simply x. So I will evaluate x from 4 to 7. So plug in the 7, plug in the 4, and we get our answer. It is 3. Example 8. Now, this function, does that look a little familiar, that integrand? You have seen it before, and its antiderivative is tan inverse of x. So let's take tan inverse and evaluate at 1 and 0. So I plug in a 1, tan inverse of 1 minus tan inverse of 0. And tan inverse of 1, well, what is the angle that gives us a tangent of 1? That's just an angle of pi over 4. And tan inverse of 0 is 0. So there's our answer, pi over 4. This graph has kind of a neat shape. It's a hill that crosses right over the origin. And so it's kind of interesting to know that this function between 0 and 1 has an area that's exactly pi over 4. All right, 1 over x. What is an antiderivative for 1 over x? Do you remember? Maybe natural log? Now, officially, it's natural log of the absolute value, but the only values I'm going to be plugging in are positive, 1 and 10, so I don't have to worry about absolute value. 1, 10. So natural log of 10 minus natural log of 1. And I want to do one more thing. What is it? There's something else I can do. This is simply natural log of 10, because the natural log of 1 is 0. All right, finishing up. 3 more examples. Compute 1 to 5 6t dt. Oh, so this is a crazy problem. All I've done is, instead of using x's, now I've changed to t's, but it's exactly the same idea. So what'll it be? Antiderivative for 6t, how about 3t squared? 1 to 5. So plug in the 5, 3 times 75. Plug in a 1, minus 3. Oops, I got ahead of myself. 3 times 25 minus 3. So 75 minus 3. How about 72? Now what's going on here? Something strange. The integral from 1 to 5 of 6t dz. The dz tells me that z is my variable, and so t is a constant. So treat this whole thing just like a constant. If I'm integrating a constant, say 4 dz, then what'll I write? This will just be 4z from 1 to 5, because 4z is the antiderivative of the constant 4. So the antiderivative of the constant 6t is 6tz evaluated from 1 to 5. Now sometimes it can be confusing, like the 1 and the 5, what variable should they be plugged into? We know it should be z, but just to make things extra clear, sometimes you see z equals 1 to z equals 5, something like that. So now I know I can plug in 6t with 5 minus 6t with 1. So that's 30t minus 6t equals 24t. And there's my answer. So it just has a variable t in it. That's okay. This last example is maybe my favorite example of all. Let's integrate from -1 to 1, x to the -2. So be really careful with our negative signs. Antiderivative for x to the -2, negative x to the -1. And I will evaluate from -1 to +1. So I won't evaluate yet, but just let me write this as a fraction because it'll be easier to see. This is x to the -1 is the same thing as 1 over x. So I'm evaluating -1 over x from -1 to +1. All right, so I plug in the +1, -1 over +1, and then I subtract, and I plug in the -1, 1 over -1. Be very careful simplifying. This looks like -1 minus, and then negative makes it a positive 1. -1 minus 1 is -2. And that is not the correct answer. Something went wrong. And I want you to figure out what it is. But I will tell you, definitely, the answer to this problem is not -2. All right, I've done some examples. Give the homework problems a try. Do the worksheet. The answers are in the worksheet, so check your work right there as you go. Get a good feeling for this, and let me know if you have questions.